Hello children, welcome to channel Sube. Children, today I am going to discuss question number 8 from the MCQ part of 2022-23 Physics new syllabus paper. The surface temperature of the sun is 6000 Kelvin and it emits blackbody radiation at peak wavelength 500 nanometer. For a blackbody with a surface temperature of 10,000 Kelvin, what will be the value of peak wavelength of emitted radiation? The first answer 30 nanometer, second one 300 nanometer, third one 500 nanometer, fourth one 600 nanometer, fifth one 800 nanometer. So children, what is a blackbody? Let us go to our lesson. So blackbody is something like this. Any space which is almost wholly enclosed approximates to a blackbody, and since a good absorber is also a good radiator, an almost closed space is the best radiator we can find. A form of blackbody which is used in radiation measurements is shown in the figure. So this one is a blackbody. It consists of a porcelain sphere. So this one is a porcelain sphere. So let us name it. So it is a porcelain sphere. S is the sphere with a small hole in it. So there is a hole here. The inside is blackened with soot to make it as good a radiator and as a bad reflector as possible. So to destroy the shining, what they do, blackened with soot to make it as a good radiator. The effect of multiple reflections is then to convert the blackbody from nearly black to very nearly black indeed. The sphere is surrounded by a high temperature bath of for example molten salt. The melting point of common salt is 801 centigrade degrees. So this is a blackbody. When it is heated, suppose to 6000 Kelvin as in the question. So if this sun is at 6000 Kelvin, it radiates from this hole, various wavelengths, radiations of various wavelengths like this. From this opening there will be various wavelengths of waves. So if we plot a graph after measuring those wavelengths, we get a graph like this. Suppose this one, suppose this there are various graphs here, you see. So this one refers to 1000 Kelvin, this way, this graph. So this one is higher, 1260. So what happens? The peak moves to left. Left means to lower values of lambda. So these are lambda. This x-axis is lambda, wavelength. So the wavelength decreases of the maximum intensity. So this one is intensity. To y-axis, what they have taken is intensity. Intensity, you know, the strength, the intensity. So they have taken it to y-axis. So even though there are all the types of all the wavelengths, but the intensity is different. Intensity is different between each. Among each waves, the intensity is different. Some have larger intensity, some have, that means some are very bright, some are not bright, they are dim. So like that there are various wavelengths, but and also there are various intensities. Then when we plot the graph, so we get a shape like this. So what happens, the peak, the maximum intensity, the wavelength of the maximum intensity, the wavelength from this x-axis, the wavelength of the maximum intensity, we write it by lambda m, but it is not the maximum lambda. Lambda is this axis, maximum lambda is this way, here somewhere, maximum lambda, but it is not the maximum lambda, it is not the maximum wavelength, it is the wavelength of the maximum intensity, or peak intensity. So there should be the word intensity, not just peak. So if we measure it moves to the left, that means to the lower region, it decreases. So that relationship found by who, here it is Wien's displacement law, it is called Wien's displacement law. So this one is this equation. Now we have to use to solve this problem. So what is that equation? Let us keep this aside. Lambda m is not lambda maximum, lambda m is the wavelength referred to the maximum intensity, the wavelength of the maximum intensity, times absolute temperature equals a constant. It is a constant. So constant is given by Wien, so it is called Wien's constant. So 2.9 times 10 power minus 3. So that constant we don't want for this question, because they have given two incidents. So the second one is this black body, first one is this sun. So let us write equation for this first one. So lambda m is 500. So they have given in nanometer, but the answers are also in nanometer, so no problem, we can use directly. 500 times the temperature is 6000. So we are substituting to this equation, substituting to this equation. So 6000 equals K. Then the next one, for a black body they have given the wavelength. What we have to find out is wavelength, so that we don't know. So let us write lambda m times the temperature is 10,000. That also equal to the same K. So we can equate these equations because they have the same K. So 500 times 6000 equals lambda m times 10,000. So 30 we can cancel. Then 500 times 6 divided by 10 is lambda, that is the lambda m. So cancel. Then 0 300 yes, here is the answer, 300 nanometer. So that is the answer. So children, this question is not a difficult one. If you remember the equation, this one, Wien's equation, you can answer this question easily. So this is so you must have learned these things. They must be there in your notebook. So just you have to use this equation. Children, I think you are happy. If you are happy, you have to make me happy too. You know how to do it. If you haven't still subscribed my channel, you have to subscribe it before you leave the page. and also press the bell icon and press the thumb up icon, and also share my link among your friends. Then see you tomorrow at 6 o'clock in the evening. Goodbye, children.